Good morning. Thank you for joining the final webinar in our 6-part Open-NFP summer webinar series. Today, Johann Tönsing is going to present Stacks and Layers, integrating P4, C, OVS, and OpenStack. This webinar will discuss the growing trend of using SmartNICs to offload networking tasks from server CPUs to free up cycles for application processing. It will compare how this can be accomplished programmatically via languages like P4 or via existing data plane implementations like OVS. A copy of the presentation, archived replay, as well as any project code will be made available shortly after the webinar. These, as well as our previous webinars, can all be found on the classroom page of the open-nfp.org website. Johann Tönsing is the Chief Architect and SVP of Software at Netronome. Johann is an industry expert in SDN, Linux-based networking technologies, network virtualization, security, and NFV. Johann has been an active contributing member in multiple standards bodies related to SDN and NFV. As Netronome's chief architect, Johann leads all aspects of Netronome's product design and development, with heavy emphasis on advanced and open server-based networking technologies, where he also holds multiple patents. He holds a Master's of Engineering in Electronics. Let me describe Open-NFP before I turn it over to Johann. Open-NFP's objective is to support and grow reusable applied research in data plane network functions processing. We do this by focusing on reducing the barriers to performing research in this space to researchers and developers creating, implementing, and verifying their ideas on production networking hardware. Open-NFP supports research in a wide range of technologies, including software-defined networking, OpenFlow, vSwitch, and P4. We support researchers with a variety of tools, including deeply discounted hardware, IDE software, and cloud access to deployment systems, and direct support from our engineers and a research community. We also provide support to learning advanced networking concepts on our hardware through tutorials and seminars such as this one we are performing today. We encourage proposals to research funding agencies. We invite you to join the 20+ universities and companies working directly with Open-NFP through projects. And then for this webinar, for questions, please type them into the GoToMeeting chat window, and we will answer those either during the session or after Johann has presented. So thank you. Take it away, Johann.
Hi, everybody. So today we are going to cover a review of the traditional cloud networking stacks. In this part, we'll look into how OVS is architected with and without connection tracking, something you may not be familiar with called Control-V router, which is an equivalent to the OVS virtual switching technology, how SRIOV is working, VirtIO, etc. The issues we will be considering include flexibility and performance, as well as CPU utilization of these traditional technologies. Then we'll go and have a look at how to accelerate and offload these cloud networking technologies using SmartNICs, going into a lot of detail on the implementation, looking at the hardware that it runs on, in other words, the SmartNIC, as well as how exactly the software works. All of this is possible by using the traditional cloud management systems like OpenStack. Once we, however, introduce additional programmability using mechanisms like the P4 and C languages or the eBPF extensibility mechanisms in the Linux kernel, we need to modify these stacks like OpenStack or any other cloud management stacks. So we'll look into different options for such extensibility and the implications of that on the cloud management stacks. Finally, I'll have a few performance results as well as an update on various open sourcing and integration activities to clarify how these changes that are needed to the stacks will be deployed into the open source community. So I'm hoping that you'll have a lot of interesting questions for us at the end. I'll try and leave enough time for questions. So starting then with the traditional networking options, one option that is of interest primarily to the NFV community is using SRIOV with a regular, or as we call it, a dumb NIC, politely, to direct the traffic to the SRIOV endpoints. So in this case, one needs a vendor-specific plugin in OpenStack to go and set up the SRIOV-based forwarding. In this case, the forwarding intelligence is quite limited. NICs support things like VLANs or maybe MAC addresses to be matched and then use the MAC address to direct the traffic to a certain VM. Maybe a VLAN tag can be used combined with a MAC address or alone as a key in the lookup tables to direct the traffic. Typically, this solution does not support tunnel termination. And therefore, if you do want to do overlays, you cannot do it with a NIC alone. You may be able to do it with an external switch. Furthermore, this solution will not support security groups or firewalling of any kind. Another option, though, is to go and deploy something like vSwitch. In this case, the OpenStack control plane integration uses an ML2 plugin, potentially feeding some of the control to an SDN controller, potentially going direct to your compute nodes. An emerging new option is to use the OVN plugin and using OVN across the data center network to get to the compute nodes instead of OpenFlow. In that case, the OpenFlow runs only locally in the compute node. The forwarding in this case can be more extensive because you have all the expressiveness of the OpenFlow match action tables. However, in practice, what OpenStack typically uses is L2L3 based forwarding. It doesn't leverage all the expressiveness available in OpenFlow. Overlays become possible with a variety of tunnel protocols. VXLAN and GRE are well established, with OVN making Genève the default protocol. That's also emerging now. For NFV applications, service chaining, etc., NSH is another emerging tunnel protocol. As far as security goes, the latest OVS releases 2.5 and the emerging 2.6 can interface to the Linux connection tracking module to implement security groups. It's still possible to go and have security with the older releases by leveraging the IP tables, NF tables next to OVS. The other option is, as I said, vRouter instead of vSwitch. This similarly has plugins and drivers in OpenStack. It similarly, even though there's potentially more expressiveness available, uses L2L3 forwarding tables. The difference to OVS is that in vRouter, your forwarding and your policies are completely decoupled. So the so-called flow table in vRouter handles your policies and then also your security groups or your firewalling. The details of the supported tunnel protocols are also a little bit different, but in general they're conceptually similar, so I'll treat them as similar in the remaining slides. There's some other options like load balancing NAT, etc., that we're not getting into here, that are also additional options available in vSwitch and vRouter that's not available in the SRIOV case. So if we go and evaluate these technologies, as far as the traditional SRIOV approach goes, as we saw, there's very limited expressiveness. You cannot go and do general match action to direct traffic. You can maybe match a MAC and a VLAN tag. You cannot do tunnel termination or stateful forwarding. But the NFV community still likes this approach because you get high throughput. You could, for example, map a certain port on a NIC with SRIOV through to a VM running a DPDK application, and then run your VNFs with this high throughput. The cost of that, though, is because you do not have the switching integrated, you need to deploy external switches on your network to do your switching intelligence. Furthermore, with the SRIOV solution, you cannot go and migrate those VMs, potentially running the VNFs to other places. With the OVS and vRouter option, conversely, you have very high expressiveness. You can do many match action rules, terminate tunnels, do the firewalling you want. However, the throughput is limited, and the CPU utilization is quite high. In some cases of high network throughput, using half of the server's cores just to do the virtual switching and forwarding of traffic to the VMs. If we introduce SmartNICs, we actually get the best of both worlds, because a SmartNIC allows us to do the data delivery to the VMs using SRIOV. So you can still run your DPDK-based or kernel-based application, tie it to an SRIOV virtual function, while offloading all the virtual routing and virtual switching to the NIC, including tunnel termination, firewalling, etc. Furthermore, the SmartNIC allows you to do VirtIO optionally, and therefore support VM migration, which is something that basic SRIOV cannot do. As far as comparing the SmartNIC accelerated approach to OVS and Control vRouter, it's identical in terms of the expressiveness, because the NICs have the ability to run all the data path intelligence on them with higher throughput and lower CPU utilization. So only using a fraction of a core rather than potentially half of the cores in the system to achieve this. So we'll look at all of this in a lot more detail in the following slides. Examining quickly the hardware that is used to achieve this, the Agilio CX SmartNICs are low-profile cards, half-length, with the power and connectivity one would expect, less than 25 watts, 10, 25, 40 gig, etc. They're based on flow processor silicon with a large number of cores, each with a number of threads. So in the end, you get 500 on the low end, more than 1,000 on the high end chip threads, processing packets in parallel. That gives you quite high throughput, because these NICs do not just rely on the memory on the chip. There's actual external DRAM. There's enough memory for lookups tables or state tables to support millions of entries. And combined, therefore, these NICs have the ability to fully offload the existing data planes. Let's look in a bit more detail at exactly how that's done and how the integration is done with the existing cloud management systems like OpenStack. So the first step would be to download the required forwarding or security policies And this is typically done directly from OpenStack, using its components like Nova for the compute, Neutron for the networking. Optionally, SDN controllers like OpenDaylight or any other OpenFlow SDN controller can be incorporated into the path. That's typically done if you also want to use SDN to control physical switches in the network. For basic OpenStack deployment, an SDN controller is not necessary. The Netronome NICs also support callable APIs, and as any OVS, there's an OVS command line interface as an additional option, but they're typically not invoked in an automated fashion in the clouds. The SmartNIC is then inserted into the data path and is able to fully offload the kernel data path of OVS. So if there's match action capability in the OVS kernel data path that's replicated onto the data path implementation in the SmartNIC, the action processing is also replicated. Actions here include drop or count, in-tunnel, deliver to the VMs with SIOV or VirtIO, etc. If a packet arrives and it notices that there's no table entry that the packet can match it will send that packet to the host, and we call that fallback processing. The host will then go and notice, typically first bucket in a flow, that it's not in the OVS kernel table either, and send it on to user space. User space OVS will trigger populating the kernel table. The kernel table here acts as a cache for the user space, for the most used flows to speed up processing. So that entry is offloaded into the SmartNIC, and the SmartNIC therefore acts as a further cache or a further fast path of the kernel, thereby speeding up any further traffic processing. So this approach allows us to retain compatibility with the existing OVS, while if there's any functionality not implemented yet on the SmartNIC, being able to fall back to the existing code. For the functionality that is implemented on the SmartNIC, this already gives quite high performance. We introduce another level of caching. So this is now the third level of caching in front of this match action data path. And this involves a self-learning table that tracks every microflow in the network. This way, the OVS tables that are masked exact match tables that involve repeated lookups of a packet can all be collapsed into a single lookup per packet. And that is how the optimal performance is achieved. OVS also features from 2.5 an interface to the Linux connection tracking module. And that is also offloaded onto the SmartNIC in a compatible way, where the table entries are synchronized. So this is a lot of detail here, but the summary is that whatever functionality exists in the existing Open vSwitch is offloaded to the SmartNIC for the traffic types that are expected to occur frequently, like IP, TCP, UDP, tunnels, etc. Or using the fallback mechanism, traffic types that occur rarely, like ARP, or sent back to the normal vSwitch subsystem on the host for processing. And this way, then, it's a fully compatible implementation of OVS, just with acceleration. vRouter operates very similarly, where you have the flow classification and the forwarding separated, as I indicated earlier. The small difference is that the forwarding table with vRouter is preemptively copied. It's not driven by the first packet in a flow. The forwarding table should already be set up when a first packet arrives. However, the flow tables are handled using the table causing a miss involving the host kernel and user mode code, causing the entries to be populated in the kernel and onto the SmartNIC, similar to the OVS case. So to contemplate the characteristics of these data paths. So as we saw, the existing server data path behavior is replicated onto the SmartNIC. So whatever functionality is available in the existing data path is now the flexibility that's offered. One can go and configure match action tables in the case of OVS in order to do your forwarding and policies together. In the case of Contrail, your forwarding and the policies are separately handled, but all those capabilities remain available. The integration is performed using plugins and drivers. For OVS, you have the two options we discussed, the OVN driver or the ML2 plugin for OpenFlow with or without SDN controller being involved. vRouter also has a driver available for OpenStack. So the only new thing that one needs to do in the integration area here is to extend OpenStack to support the concept of SIOV combined with virtual switching being offloaded. Because the existing, for example, ML2 plugins do either OVS or SIOV in a vendor-specific way. So these small changes to the plugins are being made available open source by Netronome to fully leverage all these capabilities. If we now start to think about more customizability, we must realize that these SmartNICs are not furnished with firmware in the factory, which is kind of burnt into them. The firmware can be dynamically changed, dynamically downloaded. The firmware can go and implement the existing systems like OVS Contrail, or for that matter eBPF, in the Linux kernel. In that case, all the functionality and all the behaviors that are possible will be determined by whatever you are offloading. One can, however, also develop the firmware in languages like P4 and C. In this case, you have a traditional integrated development environment where you can go and edit code, compile it, debug it. There's even a simulator, etc. So this is the normal software development process that you follow to go and develop the firmware. The remaining part of the presentation covers how to exactly do that and how to integrate these custom programmed data paths into the pre-programmed host offloading, host behavior replicating data paths that we've just discussed. So we heard here P4. For those of you that are not familiar with the language, this is an example in the P4 language. It's a domain-specific language for networking. You can declare headers very conveniently with arbitrary bit counts for the fields. One can then define parsing This one just passes the Ethernet layer. It's possible to go and select which next level parser to do based on the value of a protocol field. For example, for Ethernet, one would effectively do a case statement based on the ether type to then select whether to pass IP or ARP next. Then one can declare actions. This one does a drop action and a forward action. Forward action is just modifying the egress port. And then this program matches the ingress port and allows one to, using table entries, pick either the forward or the drop action. So as you can see, this is very much declarative what should be done and not saying how it should be done. It's very convenient for expressing matching, for defining custom protocols. Using this language, or using C, which I'm assuming people are already familiar with, so I'm not putting a C example on here, one can go and implement protocol independent forwarding, which really means dynamically definable protocols. So let's have a look at how that compares to the traditional OpenFlow. With OpenFlow, your protocols are predefined by the OpenFlow specification. The OpenFlow specification also specifies the overall layout of the pipeline in the switch, the overall match action behavior. For example, the fact that there's a number of flow tables, you can only go forward, you can't go back, there's a group table, meter table, etc. That whole layout is defined by the OpenFlow specification. And that is then what something like vSwitch would go and implement. If we did want to introduce a new data plane protocol, we would have to create a new version of the spec or do an appendix, is a new way of doing it, do an extension to the specification and then go and implement it. The idea with something like P4 and other protocol independent languages is that you just get a blank slate for the switch. There's no knowledge built in as far as the protocols and behaviors goes. There's no knowledge built in for things like which tables are arranged in which way, where does quality of service occur, where does metering occur, etc. So it's even possible to do your quality of service in the middle of the pipeline if you so choose. Using a program that's written in a high-level language, for example P4, which is then compiled down to the target platform, the protocol parse tree becomes defined. The match action table structure becomes defined, which actions are possible, packet metadata. All these things can be expressed in the program. But you would still need a management and control system. So you would need a southbound interface from your OpenFlow controller for runtime population of the tables, for handling statistics and events and the like. And if you want to now go and introduce new data plane protocols, the existing OpenFlow runtime interface would not be able to cope with such new protocols unless we extend it. That's why this diagram refers to an OpenFlow++ as a new potential runtime. Furthermore, knowledge of that may need to also be added to OpenStack. So for example, OpenStack would have a GUI allowing you to assign an IPv4 address to a VM. If you define the concept of an IPv8 address because IPv6 doesn't have enough bits or something, then the OpenStack side would also need to be able to enter these new addresses for your data plane protocol setup. So how can we leverage this technology without having to completely change all the existing systems? Existing management stacks, existing layering of user mode, kernel, etc. One way would be to simply have a plugin into the existing data paths. So we could define the concept of a data path extension that's in burgundy on this diagram, and that could be implemented in this P4 language we've just seen. Netronome also supports C as the language in which these can be coded, and they would then be put alongside the existing OpenFlow, vSwitch, vRouter, etc. data paths. So now the implication of this on the stacks varies according to exactly how this is modeled. If you simply use it to implement a custom action, for example, filtering or modifying the packets, that's fairly easy to integrate, because you can then potentially just make sure that traffic is sent to that custom action. If you want to use this new language to implement custom classification, it becomes a bit more difficult, because, for example, if you want to use this as an additional criterion to be added to the existing table entries that match based on other criteria, there needs to be a back and forth between the plugin and the existing OVS or vRouter matching algorithms. Furthermore, it's easier to use this to implement the inner protocols, where the idea would be that something like OVS would match the outer protocols. For example, say this is an IP packet and it goes to a certain reserved UDP port number. And then the extension could go and look at what's inside UDP, maybe do a custom tunnel or custom telemetry based on the content. If you want to go and implement the outer protocols this way, you would need to teach the existing thing that you're plugging into about those outer protocols as well to some extent. So if we integrate it as a custom port, it would behave very similarly to if that port were a physical port, because packets are sent to that port to get the packets to this custom function. And from a controller perspective, therefore, it just has to use a different port number. So maybe not that many controller code changes are necessary to invoke the plugin. If we model it as a custom action, it's kind of a finer grained option where you could do this action and continue to do some more OpenFlow actions afterwards. So it gives you more control. However, you now need to change the OpenFlow protocol, change the controller and the compute node OVS side, potentially change the higher layers as well. The next possibility of integrating P4 would be to go and generate the SmartNIC data path using the P4 language. In this case, you would not code that in something like C or similar general purpose languages, but you would use this domain specific language to generate the data path of the SmartNIC. The easiest would be if whatever you generate is still able to replicate the behavior of the upstream OVS and fall back to it. And if you do it that way, you get some flexibility, because if OVS changes, if I come up with a new tunnel protocol, then you don't need to write that new tunnel protocol from first principles. You can use the high productivity language like P4 to go and implement it. However, something to be considered here is that in OpenFlow, there is a difference between the flexibility of the table matching versus something like P4. OpenFlow, you can at any time introduce a flow mod that says a certain table can now match a new field as well. And simply by starting to match that new field, the assumption is the OpenFlow table will do what you requested. Whereas in something like P4, your table overall structure, the fields it matches, the actions it can execute, is predefined. In OpenFlow, similarly, you can introduce a new action to be executed when a match occurs. P4, that's all predefined. So that is a complication with following this approach. Furthermore, we can of course not now use P4 to upgrade what the host does if the P4 is limited to the SmartNIC, as we saw in the previous diagram. The integration effort would be modest, because if we're just offloading existing OVS code, the way OVS is integrated into the OpenStack data path can just be reused. If we're enhancing OVS, then of course that has to be taken into account as integration effort. Now let's have a look at what are the characteristics if we introduce P4 into the OVS data path also on the host. For simplicity here, I pretended that the data path is limited to the kernel. In actual fact, some of this data path change would also be introduced in OVS user space. But in this case, you would go and have a P4 generated data path on the SmartNIC as we had it before. You would also have the P4 generated data path in the kernel and the part in user space that does data path processing. And you could still use the fallback approach to let these different data paths work together. But now, at least when you're going and introducing a new data plane protocol, you could use the same code in the host side and in the SmartNIC side to go and implement that. The same with different behaviors, etc. So the functionality, therefore, is now quite nice as far as that characteristic, because you can use the high productivity language on the host and on the SmartNIC. However, this issue of OpenFlow matching being more flexible continues to be there. So to go and still support OpenFlow, one could go and regenerate the data path program whenever you see a new field being matched in a table, whenever you see a new combination of actions being invoked by a table, you would go and recompile both the host and the SmartNIC side of the data path to be able to cope with that. Another option would be to go the other way and say we want to go and assume a certain model. This would actually work quite well for something like OpenStack, because we would say we know OpenFlow does not use all the match action functionality that's available. It is only going to do the L to L3 forwarding, even though it could in theory have done more. And then we just declare such an assumed model. Schemas like the Open Networking Foundation table type pattern could be used to go and express such models, or one could effectively do it in a language like P4 by having just part of the P4 language be used for that, similar to how a C program's interface can be represented by a header file. The integration effort of this would be considerable. One effectively needs to re-implement OVS on P4. There is actually an activity underway at a university and at VMware by an intern to go and do just that, but it is a considerable effort to go and do it, and it does have these expressiveness concerns. Once the infrastructure is in place, the further evolution to new data plane protocols does become easier. Let's now have a look at if we go even further and if we get rid of the OVS user space code as well. In that case, the user space code would all be removed. There is no more OVS CLI or API because that's all gone. Even the protocol that's used to communicate with OpenStack can be discussed. So you may still have something like Open Daylight if you put a plugin into Open Daylight to go and speak with this new system. You could have a protocol like JSON RPC, similar to OVSDB, do all the work. You could use Apache Thrift, Google Protocol buffers. It could even be a callable API as an interface rather than a protocol, because the model being discussed in the community is to supply a driver as a library and make the standardized item an API. And then your protocol is just implemented by your driver. You can change a protocol at any time. Whatever the cloud management system or SDN controller needs, it can do just by calling that supplied driver or supplied library. So in this case, you have these issues with the API. You also have issues with downloading the actual programs to the target platforms and scheduling the VMs to run on nodes with appropriate hardware that can appropriately run these different programs. That discussion is underway with the OpenStack community to make the required changes. So some of these blocks here say P4, but the diagram is exactly the same. If you would, for example, say, let's use eBPF instead of P4. You could have a custom agent configuring your eBPF-based data path to go and do whatever is needed. And in fact, P4 is sometimes implemented using eBPF. And that eBPF on the host could be offloaded onto the SmartNIC as well. So to summarize this option, this gives us the full flexibility to easily implement behavior. However, with that great power comes the great responsibility that we now have to do a full custom integration. Change OpenStack, maybe even change Open Daylight if we still want to keep it. Completely new protocols and APIs become necessary to go and make this work. So here's just an example of that was demonstrated at a recent conference to show what one could achieve this way. One could have some matching, certain VMs performing certain functions, but also what we call a micro VNF on the SmartNIC implemented in C or P4 do some processing, security filtering, timestamping, etc. So here you can basically make an arbitrary topology of functionality, but it's up to you to go and integrate it with the control layers. Just a few comments about performance. So we saw the OVS kernel space option, the unaccelerated, in some of the diagrams. Here's an example of the throughput we achieve with that OVS kernel space. Roughly 5 million packets per second. There is another version of OVS, not shown in the diagram so far, which runs in user space on DPDK, that does have higher throughput available. But the offloaded OVS is having the best performance still. It can offer 5 times the throughput. However, if you look closely at the diagram here, you'll see that the offloaded case achieved this with 1 CPU core, or actually a fraction of a core, where the other cases were achieved with 12 CPU cores. In other words, 1 entire socket of a 2-socket system. So this shows why it's very important to not just consider the host-only side, why the SmartNIC offloading of these various options is quite compelling. To normalize it to a single server CPU core, we get what we call the efficiency, the work done per such core. And the efficiency can be 20 to 50 times the existing solution, because a typical rack is not only doing networking. It doesn't mean that you can necessarily replace 50 racks with one. Could be if it's literally just a network-to-network situation. But in practical cases, we're finding that you can maybe replace 3 to 6 racks with 1 rack. And if you want more information, please search our website for the ROI calculator. And you can plug in your own numbers and get the result for your case. So that's really why we are considering all these things in the context of SmartNICs, because it is a compelling benefit to go and deploy SmartNICs in these cases. So finally, just a summary of the activities related to what we discussed in the open source community. The basic drivers that are necessary for making all of this work are being upstreamed. In some cases, they've already been upstreamed. These are the Linux, FreeBSD, DPDK, etc. drivers. And they allow you to do the core plumbing of the packet paths that we saw to the host and to the guest. The Open vSwitch acceleration is being upstreamed as well. The process started 2 years ago already. And OpenStack, similarly, these plugins that we saw to allow you to have SIOV capabilities together with virtual switching offloaded to the SmartNIC. These are all also being upstreamed. You can look at the OpenStack site for RFE about this, for example. Similarly, the things we briefly touched on, like this runtime API that could potentially replace OpenFlow, that is being progressed in various standards bodies and open source communities. eBPF acceleration is also being progressed. So please contact us if you're more interested to get involved. We really appreciate feedback and also just testing of these bodies of source code. So to summarize, we saw that it's possible to go and use these SmartNICs with existing data planes, OVS, vRouter, etc. eBPF, we didn't talk about a lot, but it's a work in progress. Can also already accelerate eBPF. It's possible to program the SmartNICs. One could go and just use APIs on the x86 side to get some more programmability, but you could also program the SmartNIC itself using the and mechanisms that we've just detailed. So either way, the use case is compelling here to use the SmartNICs to get better performance, free up server resources. So with that, we can cover any questions people may have.
Johann, we haven't seen any questions, so I think we'll give it, oh wait, there we go. No, Rick Bauer says, nice job. I think with that, thank you very much. And that, again, this will be posted for the replay and the slides on the classroom page at open-nfp.org. Thanks, Johann.
I'll leave a few more minutes in case people just think of questions right now.
That sounds good.
Okay, if the audience doesn't have questions for me, I'll turn it around and have questions for you. You can use the chat to go and put in your response. Which of these different data path options would the attendees find the most interesting? Just take existing OVS or vRouter and use that in the cloud, put in a plugin, P4C code, into an existing data path, or fully program your entire data path yourself. Okay, I think people are finding all of these options compelling because they don't want to decide on any one of them. So the good news is that Netronome does support all the different options, and we look forward to your making use of that. Thank you then.
Again, thank you, Johann. Have a good day. Thanks, everybody.